This video lecture explores three different common kinds of radioactive decay, and then we'll talk a little bit about half-life as well. Okay, so then we have a couple of different kinds of decay. So how does that energy fly out from the atom when we have radioactive decay? The first kind of decay is called alpha decay. And this occurs basically when essentially a helium nucleus leaves the original molecule. So you have two protons and two neutrons. This is called an alpha particle, and those leave. So what is that going to change? Well, it's going to change your mass number, right? Because you're going to lose 4 nucleons. But it's also going to change your atomic number because you're losing 2 protons. So that we can write an equation like this, and here we're describing radium decaying into radium. We're going to go from 211 to 207, and we're going to go from 88 to 86. That's losing those 2 protons. And because we've lost 2 protons but haven't lost an electron, we now have a charged particle, right? Because we still have 88 electrons, which means that we have a -2 charge on our atom. And our helium nucleus that flew away has 2 protons, but it doesn't have any electrons. So it has a +2 charge. So this is how we would write, this is the notation we'd use for an alpha decay. And you're going to see those relations, anytime you see that alpha decay, you'll have the same relation. It's going to be -4 for the mass number, -2 for the atomic number. You're going to end up with a positively charged helium nucleus flying away, an alpha particle, and a negatively charged element. So how could we write that in a general form? It would look something like this, where this is the number of neutrons here. And essentially that's just what we've talked about there. So make sure you can look at that and understand that if you need to pause. Okay, so alpha decay, that's the third type of decay that or second type of decay we'll talk about is beta decay. And this changes the type of an atom without changing its mass number. How does it do that? Well, a neutron in the nucleus is transformed into 3 particles, a proton, an electron, and what's called an antineutrino. So if you look at this, you can see that the mass number is going to stay the same because a neutron and a proton are both going to add 1 to that mass number. But our atomic number is going to go up 1. Also notice here that the antineutrino is an uncharged particle. And that means that the conservation of charge holds. We have a 0 charge in our neutron, and then we have a 0 charge between the proton and the electron after decay. So we can write that decay this way, where we have the mass number after the decay stays the same, 40 and 40, but the atomic number goes up from 19 to 20. And when the atomic number goes up, the type of element changes, right? So we go from potassium to calcium here. And then we eject an electron, and then this is the sign for an antineutrino. An antineutrino is a chargeless and weightless, or nearly weightless particle that basically balances the angular and linear momentum of the exchange and moves at nearly the speed of light. And so it's took a long time to be able to actually identify that this was happening, and then to find one was even harder. This beta process can happen in reverse, okay, in which case a positron is released rather than an electron, and a positron is essentially an electron with a positive charge. So you can start to see that when we get into particle physics, you'll start to see all sorts of different particles that you didn't learn about in high school. In high school, we got the electron, the proton, and the neutron. There are a bunch of different particles at the particle physics level that are outside of those three, the three big particles. A lot of them don't last for very long or are extremely hard to detect for various reasons. And so it's taken a long time to really um, nail down what those are and how those different things behave. Um, so notice that this image over here on the right, that the individual decay of alpha and beta oftentimes happen in a series. So over here, we're going to start with uranium-238. Um, and you can see as this chart goes that anytime you have an alpha decay, what's going to happen? Well, we're going to lose two um, of our atomic numbers. So here we go from 92 to 90, I think. We're also going to lose two neutrons, and that over here on the left is how many neutrons we have. And so we lose two neutrons there. If we have a beta decay, we're going to gain a proton but lose a neutron. So it's always going to be an arrow in this direction as we gain uh, another proton, right? So here in this alpha, we lost two protons. Here we gained two protons, and we're back to uranium. And then we can go through a bunch of different alpha decays and eventually get down to an element that's quite different than the one we started from. Uh, these numbers here are our half-lives, and we'll talk about those next time. But essentially what that means is how long does, it gives us a sense of how long it takes for this decay to happen. If I have some uranium-238, how long does it take for it to get to turn into Th234? As you can see here, a long time, right? But some of these, as you get down here, it's going to be very, very fast, like 35 milliseconds here, 2 seconds. So the range of our half-lives, how long does this take, cover a really big range. And finally, the last type of decay that we'll talk about is gamma decay. Um, Basically, this is a change of structure inside the nucleus. So we're not going to write it in the same way that we did with those other equations. But basically, you might think of it as the nucleons moving to a different energy level. They shift around, and that changes how much energy is in the nucleus. With this change in energy, a photon is ejected, and a photon that has a very high energy level. What does that mean? Well, it means it's a really high frequency, right? Um, and that gamma decay, that gamma particle, means that it can penetrate substances um, such as human tissue or biological tissue, and that makes it dangerous, right? But also something that we use in things like cancer therapy. So those are the three main types of radioactive decay, um, and that's as deep as we're going to go in this class. So what is a half-life? We mentioned this last time. It's basically an indication of how long it takes for a particular kind of decay to happen. But there's a more technical definition of that that we'll get to here. This comes from, again, when we deal with quantum, we're almost always dealing with probabilities. And so if we want to predict when a decay is going to happen, it turns out that it's nearly impossible to do. We can predict when a bunch of decays happen because those probabilities will all sort of cancel each other out. But in terms of choosing when one actual decay is going to happen, it turns out that it's somewhat random. It's not totally random. It's governed by a probability law, but we can't pick out that one decay. When we have a larger group of nuclei, we can start to see the patterns that are created by that probability. This tendency that shows up in large groups is where half-life comes from. A half-life is the length of time it takes for half of a large sample to decay. Or another way of saying that is there's a 50% chance that an individual nucleus will decay in the span of a half-life. So if I have let's say a kilogram of uranium-238, And I can see that my half-life here is 4.5 times 10 to the ninth years. And I want to know how long it's going to take for that kilogram to turn um, into this other molecule here. Um, Basically, I can say that half of that uranium, in other words, half a kilogram, is going to decay over the next 4.5 times 10 to the 9 years. Um, then I'd still have half a kilogram left. So how long would it take for that half a kilogram? Well, half of that would decay over the next 4.5 times 10 to the 9 years. So after 9 times 10 to the 9 years, I'd have about a quarter kilogram of uranium and 3/4 kilogram of this new molecule. As we mentioned last time, there's a huge range of half-lives in a decay cycle like this. So it ranges from, trillions of years down to milliseconds. This is another instance of an exponential behavior that we talked about when we talked about uh, like capacitors and inductors in circuits. Um, and that exponential decay means that the rate of decay depends on how much stuff you have. Okay, so the number of, well, you can put this in a lot of different ways, but the number of undecayed nuclei n, um, in other words, how much uranium, how much of my 1 kilogram of uranium do I have left, is going to be equal to the initial amount of uranium that I had, multiplied by this exponential term here. Okay, that exponential term is basically taking our half-life here, whatever our half-life is, um, uh, and then multiplying it by the time that it's actually passed. So let's say my half-life is 10 seconds, right? I might put 10 seconds here, and then I could multiply that by um, however much time has passed. So let's just do the math here. Let's say our half-life is 10 seconds and 10 seconds have passed. Then I'm going to have 0.693 over 10 seconds times 10 seconds. So these two things are going to cancel. And I'm going to get e to the negative 6.93, right? And pull out your calculator. And I'm going to type in e to the negative 0.693, and you're going to get half. Okay, so that's 0.5. Now, so if this term, when this number here is the same as the half-life, the whole exponential term equals half, right? Which means that half of the original number of nuclei now exist. Let's see what happens. Again, pull out your calculator. Let's say um, our half-life is 10 seconds and we've waited 20 seconds. That we're going to divide these two out and we'll get 2. So 2 times 0.693, I'm doing this here on my calculator, is 1.386. So let's take e to the negative 1.386. And we get 0.25, right? So after 2 half-lives, the original amount of nuclei have been cut in half once and then cut in half a second time. And so you can see that pattern over here. If you have 1,000,000 nuclei, you're going to have 500,000 after one half-life, 250,000 after the next, 125,000. And that's what we mean when we talk about an exponential curve in this sense, is the rate of change here. Here we're changing 500,000, here we're changing 250,000. Depends on how many nuclei you actually have, right? And that's an exponential change. So, theoretically, it never gets down to 0, although that is when you have quantum numbers, when you actually have nuclei, at some point it will reach 0. Okay. So, rather than we can use this equation to find the exact number of nuclei. A lot of times we'll think more in terms of how many times we have to cut something in half to get a certain number of nuclei. So if we wanted to know how long it took to get 1/8 then of the original material, we would say, well, that's 3 half-lives. And so if the half-life is 10 seconds, then we'd say, well, that'll take about 30 seconds. This process, you might have heard of carbon dating, and this is what carbon dating is. You have C14 that occurs naturally in animal tissue, but decays once an animal dies. So you get this really cool effect of, if you find an animal, you can look at how much C14 is in that tissue, and it gives you a sense of how long it's been decaying.